Hello, can you hear me?
Yes, sir.
Okay, fine. Anyway, I think we'll continue with the class. We shall see what to do with this issue. Okay. So we were discussing upon the bond and the factors causing bond between two materials. So right. So I hope you have, you know.
Sir, ask
Yes. Ask it, correct.
sir, join ചെയ്യാൻ പറ്റുന്നില്ല. അപ്പോൾ I think I will take the classes for my batch later. Okay.
Okay, fine.
കാര്യം അവർക്ക് കയറാൻ പറ്റുന്നില്ല, കുറെ കുട്ടികൾക്ക് കയറാൻ പറ്റുന്നില്ല. Or you continue with this 100 people, or you can continue with this 100 people and you can record the session. I think that will do.
Okay, that will be fine. Anyway, നമ്മൾ തുടങ്ങിയില്ലേ, നമുക്ക് record session.
Okay. Those who are interested can be in the class. We will not monitor the attendance for today's class. Okay, we will give the recorded session also.
Okay, fine.
Don't simply sit for the sake of attendance. Those who are interested can join, please. So thank you sir.
Okay, fine. So we have cohesion and adhesion, right? So I hope you know the term cohesion. Cohesion is between the bond. If the bond is caused between two similar material, it will be cohesion. And if you are having two different materials, and if there is a bond between two different materials, it is called adhesion. So the first mechanism is adhesion, right? So that is due to the adhesion between the concrete and steel, there will be a bond that makes it behave together. Right. The second factor that you might be familiar, that is called the friction, right? Or this, you can term it as frictional resistance. Okay. So that is the second one. And so frictional resistance means you are having your material, the surface of contact will be having a roughness or some kind of undulances. So due to which the materials may have the materials will be developing friction between the two surfaces. So due to which it will be acting together. The third one is, if you have observed the surface of the reinforcement, especially the HYC bars, high yield strength deformed bars, or otherwise it is called a top steel, it will be having what you can say it has ribs. It will be having ribs. So due to these ribs, when you cast reinforced concrete, and once the concrete gets hardened, there will be a sort of mechanical interlocking, right? So you can say that the third factor that causes bond between concrete and steel is mechanical interlocking. Right. So these three are the factors causing the bond between concrete as well as steel, and that causes the action or combined action or a monolithic action of both. Right. So if you go further, in order to continue or in order to go into the concept more, we will take an example of cantilever beam. Right. You can see the cantilever beam over here. Right. See, you are having a fixed support. Right. So this is a fixed end over which you can have to which your beam is supported, and if you see that it is being loaded with WU. I have denoted that this as the ultimate load for the beam, and this load considers the self weight also. So this is WU, the design load of the beam. Right. So if this is a design load, then what will be the variation in bending moment? What will be the variation in bending moment? We shall see. I shall draw it over here. The variation in bending moment. So this will be the maximum value, right? You have the maximum value towards the support. This can be marked as MU, and the variation will be parabolic, right? So it will be something like this. Right. And you have a negative reinforcement. The bending moment will be, or BMD will be negative, right? And so as a result of which, what happens, or how to provide the reinforcement for this beam, and where it will be having the maximum value? Can anyone tell me where it can have the maximum value? So based on which you will be designing, your critical section will be at which location? From the diagram, it is clear to you, right? You'll be having the critical section at. Can anyone prompt me? Am I audible to you?
Yes, sir.
Okay, fine. So where you'll be having the critical section for this beam? Critical section means the section for which you need to design.
Fixed edge.
Pardon?
Fixed edge.
It was the fixed end, right? You have the maximum value at the fixed end, so you have to provide the reinforcement like this, right, at the top, right? So this is your reinforcement, and you can mark it as and this will be your ASC, right? You have the ASC over here, and that is based on this section. You have the fixed end, and based on which you will be designing, and you will be providing a reinforcement of ASC. And let me ask you something. So to which side you will be having the maximum tension with respect to the length of the beam? If this is the length of the beam, over to this length, you will be having the maximum tension for the reinforcement, whether to the free end or to the fixed end. Is it to the free end or to the fixed end? Definitely, you are having the maximum moment at the support. So your support, your fixed end will be having, or towards the fixed end, the reinforcement will be having the maximum tensile force, right? So what I'm going to do is, I'm going to take this in detail. Okay, sorry. Okay, so you will be having a tensile force over here, right? You will be having a tensile force over here, right? T. What is this tensile force? Can anyone tell me what this tensile force is? AST. What is this tensile force equal to? You have AST, the area of tension reinforcement. So the tensile force will be equal to 0.87 Fy AST, right? We can assume that this AST is having n bars and it is having a diameter phi. So the total AST will be equal to n into pi by 4 into pi square. Okay, so you are having the tensile force at the fixed end. So this is the tensile force at the critical section. So I am using the term as critical section over here. So this is the tensile force. And can you imagine what happens if can you imagine what happens if you are restricting the reinforcement up to here? If you are restricting your reinforcement up to here, what could happen? This is your section XX. XX is the critical section, and if you are having the reinforcement only up to here, what happens? What happens beyond that? You will be having the maximum moment over here, and if you are not providing reinforcement further, your section will be you'll be cracking, or the section fails by developing tensile cracks at section XX. So at section XX, maximum tension is available. Tension develops. That's a and it may fail to that section, right, to that particular location. So what you could do is, or what the possible way out is, you will be, this beam, it may be fixed onto a column. So I'm drawing this column over here. Right. I'm drawing the column over here. And see, you need to provide, or you need to take up this tensile force. You have a tensile force over here. So you need to take up that tensile force over here. So in order to take up the tensile force, what you need to do is you have to extend this reinforcement a little bit. Okay, you have to extend the reinforcement a little bit. Why? Because I'll explain. I'm extending this reinforcement for a length L. Okay, I'm extending this reinforcement for a length L. That is from the critical section up to a certain distance L. Okay. So I'm taking that L somewhere over here. I'm taking that L somewhere over here. So this is that length L. Okay. So whatever, I'll take it to the next page. That is better. You have your actual reinforcement. I'm drawing only the reinforcements over here. You have the actual reinforcement, and at the end of this reinforcement, you have some tensile force. You will be having the maximum tensile force. I'm marking this tensile force over here. right? And the other part of it, I'm now drawing this L over to this location. I'm separating it out, right? So this is your L, or the length that is provided beyond the critical section. So this is your L, right? The length of reinforcement provided beyond the critical section. So you need to resist. If you have a tensile force over here, definitely at this particular location also you'll be having the same tensile force, right? Now this has to be resisted by this particular length. How is it possible? How is it possible? You are having AST, right? You are having AST over here, and that equals N into 5 by 4 into 5 square. This is the AST. So your tensile force equals, your T equals 0.87 Fy into AST. So I am writing AST as N into 5 by 4 into 5 square. Okay. So that is your T. This T has to be resisted at this particular location. So that is possible by the development of bond stress on the surface of reinforcement. For what length? For a length L. You are having a length L, and you could resist this reinforcement, or you could resist this tension by the development of some stress at this particular location. Okay, so that is what I'm going to mark over here. Onto the surface of reinforcement, it will be developing some stresses like this. I'm marking the stresses which opposes the tensile force T. Okay. That occurs onto the surface of reinforcement. Right. And this is denoted as tau BD. BD denotes bond. So this denotes, or this is called tau BD. So what will be the force of resistance offered by tau BD, by the length L using this first tau BD? So the bond equals the anchorage bond. It is otherwise called the anchorage bond. Equals, and that should be equal to your T. And what is that equal to in terms of the surface force of resistance? You are having a bond stress tau BD, and it acts over some surface area, right? What is the surface area for length L? What is the surface area for length L? Can anyone tell me? What is it equal to? Tau BD into, what is the surface area? Can anyone let me know what is the surface area? You are having a length L. What is the diameter of the bar? What is the diameter of bar? You are having n number of bars. 5 is the diameter. So what is the surface area, or what is the perimeter, or what is the surface area for the bars which are extending beyond the critical section XX? I hope you know the surface area of a cylinder. Right? Yes. It will be pi into 5. Pi into 5 will be giving you the perimeter into the length L. Right? So you can equate these two. You are having 1. You are having 2. Both are same. So if you are equating both, 0.87 F5 into N into 5 by 4 into 5 square equals tau BD into L into 5 into 5, right? So from this you can find what L is. This length is what we need to find out, because we need to provide this length L beyond the critical section. So that is what we are finding it out over here. So L equals 0.87 F5 into N into pi by 4 into 5 square by tau BD into pi into 5. So you have pi cancelling out. This one cancels. Pi cancels. You have some N over here, right? I forgot to put N. Tau BD into N is there, right? I hope that I put in the previous thing. Yes, you have N over here. That N comes over here. So I have to cancel it out. Right. So this equals 0.87 F5 into 5 by 4 tau BD. Alright. So or I'm replacing this 0.87 Fy. I'm replacing this 0.87 Fy by a value or a notation called sigma S. So your length or the development length, this is called the development length. This is what is called a development length, and I'm suffixing a D to this L. So LD equals 5 sigma S by 4 tau BD. So this is your development length. It's the expression for your development length. Okay. So if you are designing reinforcement, if you are designing the reinforcement, you have to provide some length beyond the critical section for a length LD, and that LD is given by the formula 5 sigma S by 4 tau BD. Right. So this is explained in code also. It's given in this expression is given in your code also. If you refer back, you have clause 26.2.1. That is in page 42 of your IS 456. You have LD 5 sigma S by 4 tau BD, where tau BD is the design bond stress, right? So if you come over here, you are having tau BD. That is a design bond strength, right? See, design bond stress, exactly, and it is given in page, the next page, that is in page 43. For different grade of concrete, you have different value for tau BD, right? So if you come over here, you have bond. Right. Now you have to talk with respect to the code. See, there's a table over here for which you can see the bond stress, right? So if you are having the deformed bars in tension, if you are having deformed bars in tension, this value if you see, it has to be increased by 60%. If you are having HYSD bar as tension reinforcement, you have to increase this tau BD by a value of 60%, by 60%. And if you are keeping these bars in compression, then the tau BD has to be increased by a 25%. The tau BD has to be increased by 25%. Okay. This could be clearly explained with a numerical. We'll do a numerical now. Okay. So we have a cantilever beam. Please note, we are having a cantilever beam. RC beam, cantilever RC beam. If you need any clarifications, please ask. You can type in chat box. This cantilever beam is having a span of 2 meters. It's having a depth of 200 millimeter at the free end, and this particular location you have okay. This is 200 mm. Its B equals 250 mm. Okay. Sorry, width will be 200. Sorry, it's not 250. It's 200. And it is being reinforced with bar. This is two numbers of 25 mm hash, and towards the compression side it is having two number of 60 mm hash. Right. Having two number of 25 mm hash and as tension reinforcement, and two number of 60 mm hash as compression reinforcement. It's being provided with these reinforcements, and it's having a load of design load of 100 it's having a design load of 50 kilonewton per meter. Mu is 100 kilonewton meter. This is at the fixed end. At the fixed end, you have a bending moment, ultimate bending moment of 100 kilonewton meter, and you need to design the development length, or you can take it like this: provide necessary development length. You can take M20 concrete and Fe405 grade C. So this is your question. So how to proceed over here? How can we proceed over here? Will the development length for tension reinforcement as well as compression reinforcement be the same? Will the tension reinforcement as well as compression reinforcement be same for will the tension reinforcement as well as the compression reinforcement have the same development length? Is there the chance for that? Can anyone give me a suggestion? It will be different, right? So we have to define the development length for tension reinforcement first, right? You have to provide the development length for the tension reinforcement first. So how to calculate that? You have the formula for you with you, that is LD equals sigma phi sigma S by 4 tau BD, right? So your phi, what is your phi over here? What is the phi for tension reinforcement? It is 25 mm. What is sigma S? It is 0.87 into your F phi, that is 4 on 5 by 4. Now you have to take tau BD. So how to take tau BD? What is tau BD over here? Your grade of concrete is N20. So what is the value that you have to take? What's the value that you have to take? You can give it in chat box. You have to take 1.2, right? So you have to take 1.2, but your bar is HYSD. So you have to provide 60% extra, right? You have to increase it by 60% extra. So that has to be considered over here. So that will be provided over here as a factor of 1.6. So what will be the value over here? That is 1.92 is the tau BD. 1.92 is your tau BD, and substituting it, we'll be getting some value over here for as the development length. It is 1175 millimeters, right? 1175 millimeters, and please note that this is the LD required. Okay. So there will be change for this depending upon the AC provided, right? So over here, I have to give you two more data. That is, please note that the AST required is 936 mm square. And ASC required for this given beam is 266 mm square. So I am giving you these two data, so based on which you may have a difference for the a development length to be provided. So the development length to be provided, LD provided equals, you have to note this formula, that is depending upon the ratio of AST required and AST provided, you can adjust the development to be provided. Right. Your LD required is 1175. Your AST required is 936. What is the AST provided, or what is your AST provided? You have two number of, what is the AST provided? It is two number of 25 mm bars, right? And that equals 981 exactly. So you can take it as 982 mm square. So what is now what does your LD provided? That will be 936 by 982 into 1175, right? And that will be equal to 1120. So you have to provide a length of 1120 mm. Okay. Now you have a next question. How can you provide? How to provide development length? So that is a question to you. If you are having space to extend the bar, you can extend it. Do you have a space to provide, or do you have a space over here? I'll take this distance as I'm denoting. I'm taking this distance as 450 millimeters. You are having a column over here, and this distance is 450 mm. Can I provide 1120 over here as a straight bar? Is it possible? Is it possible? Can I provide it?
No, sir.
Maybe I can extend for a length. Yes. Maybe I can extend for some length. Maybe for a length of 380. I'll depending upon the cover, I may extend for a length of 380. I'm noting it as a 380. This is a 380 mm. Okay. I'm taking this length as 380 mm. What is the remaining length that I have to provide? 1120 minus 380, right? I have to provide 1120 minus 380, right? So what is the way out? So code recommends certain way out. I'll get you back to the code. See, if you come over here, see, anchoring bars in tension, clause 26.2.2.1. See, you can provide bends or hooks, right? You can provide bends or hooks so that you can provide sufficient length. So if you are providing a bend, there could be some amount of length equivalent to that, or if you are providing hook, there are some length equivalent to that. You can read it over here, bend. The anchorage value of bend shall be taken as 4 times the diameter of the bar for each 45-degree bend subjected to a maximum of 16 times the diameter of the bar, right? So that is what a bend means. So it means that if you need to provide a reinforcement, or if you need to provide anchorage length, what you could do is you can bend this bar like this. Okay, you can bend this bar like this. Yeah, we'll make it in detail. Don't worry. So coming back, so you can provide it like this. So this is what is called a bench. This is what is called a bench. Okay, this is a bench. And this portion and whatever you have over here, it is equivalent to the LD is equivalent to, for 45-degree bend, it is 4 times the diameter. If you are having a 90-degree bend, it will be 8 times diameter. Okay. That is for a 90-degree bend. This is for a 90-degree bend. So in this case, what will be then equal to? So the bend equals how much? 8 into 25, and that is equivalent to how much? It is equivalent to 200 millimeters. So if you are providing a bench over here, it is equivalent to, if you are providing a bench over here, it is equivalent to 200. So this bench provides, this is equivalent to 200 millimeters. So 380 plus 200, that equals 580. And what is the remaining? So 1120 minus 580. So remaining 540 has to be provided as straight bar. Right. So remaining 540 shall be provided as a straight portion. Right. And this length will be equal to 540. So 380 plus 200 plus 540. So your your LD provided, that is for tension reinforcement, equals 380 plus 200 plus 540, right? And that equals 1120 mm. So likewise, you can provide the anchorage length. Now you need to provide what? So that is the case for tension reinforcement. Now what is the case of compression reinforcement? Now you have to provide the development length for so what is that LD equal to? What is LD required? Sigma phi sigma S by 4 tau BD again. What is your phi over here now? It is 2 number of 16 mm bars. So your phi is 16. What is your sigma S? It is 0.87 into Fy by 4. What is your tau BD? Tau BD is again 1.2. But if it is a bar in compression, you have to increase it by how much? You have to increase it by 25%. Right. You have to take a note that your bar is. Hello, am I able to? Am I audible to you? Are you there? Getting me? Hello.
Yes, sir.
Okay, fine. So if your bar is in compression and if your bar is HYSD bar, first of all your bar is HYSD bar. So you can increase its value, the bond value by 60%. Again, if your bar is in compression, you have to increase it by, you have a 25% over here. So what will be the tau BD in this case? What is the tau BD in this case? What is your tau BD? Your tau BD will be 1.2 into 1.6 into 1.25. So this will be your tau BD. Right. So that equals how much? So your tau BD itself is 2.4 Newton per mm square, and your LD required equals what is the value coming? Please let me know what the value is. Yes, it is 6, not 1.75 millimeters. Then what is LD to be provided? Your ASC provided is two number of 16 bar. So that equals 402, right? So your LD provided will be 266 by 402 into 60 1.75, and that equals right. So that comes around 398, right? It comes around 398. Is there a space available to provide it as a straight bar over there? Your horizontal length itself is 450, so definitely you can provide a straight bar over here for a length of, you can provide it like this. So this is 398. You can provide a length of 398. So with that, your anchorage, this is for development length is fine. So if you need to provide in this beam, you can provide it the other way. Instead of providing a bend, so that is in the case of a compression, in the case of a tension reinforcement, you can provide it like this. Say you can provide for a length of You have provided a length of 380, right? You have provided a length of 380. Then you can provide a 180-degree bend, right? That is called a hook. You can provide a hook like this. Hook is something like this. Okay. So you can provide it like a hook. Right. So over there you have provided a 380 mm. Then this corresponds to how much? 90 degree per 45 degree. It could be taken as four times the diameter. So here you are having 45 degrees, right? That causes a 180 degree bend. This is a 180 degree. This is called a hook. So this corresponds to 16 times the bar diameter, right? So this itself equals 400 mm. And the remaining length has to be provided. So what is the remaining length? That is 1120 minus 380 minus 400. So you need to provide the remaining 340. Right. So remaining 340 could be provided as a straight bar beyond this. So this is the remaining 340. So 380 plus 400 plus 340, that corresponds to 1120 N1. Right. So this is another option. This is called hook. You have a bench or a hook. So these are the two ways in which you can provide anchorage for bars. Bend is 8 times the diameter, hook is 16 times diameter. Right. So please take a note of bends and hooks to be provided as anchorage. I'm talking about clause 26.2.1.1. Okay. Okay. Is that clear? Am I clear to you? Any doubts regarding this? Hiba, are you there? Hiba, Hiba undale. Okay, Hiba Abdul Kalam, are you there?
Yes, sir.
Is it fine? Am I clear to you?
Yeah, yes, sir. It's okay.
Fine. Akhil KS, are you there?
Sir.
Is it fine? Am I clear to you?
Yes, sir.
Okay. If you have any queries, please ask me. Else we need to proceed further.
Sir,
Yes. Okay.
hello. Sir, can you
Okay, then,
explain the toe BD? Toe BD,
Toe
sir,
BD.
that 25
Toe.
percentage increase.
Or that is you. This is you have. I hope you understood the equation. LD equals 5 sigma s by 4 tau BD. Right. So the value of tau BD will have to be taken from this table that is given in page 43 of IS 456. Depending upon the grade of concrete, the bond stress will be varying. Design bond stress will be varying. Is that fine? Okay, no?
Yes, sir.
Now, what is the variation from this? So, if you are using a deformed bar in the sense you are having HYSC bar, high yield strength deformed bar, your FE415 as well as FE500 are high yield strength deformed bars, or because it is having ribs, right? So, due to the presence of ribs, the design bond strength will be, design bond stress will be higher. So, in order to account for that, you have to take 60% extra from the value that is available in the table. Like 1.2, it has to be increased by 60%. So, you have to multiply it by 1.6. Your value has to be multiplied by 1.6 for bar in tension. Okay. For a bar in tension, or whatever be the bar, irrespective of the position of reinforcement, irrespective of whether the bar in tension or compression, you have to increase it by 60%. That's മനസ്സിലായോ?
Okay, sir.
Okay. Now, if you are providing the bar in compression, like we have over here, see, in this problem, you are having this bar at the bottom, and that is in tension, right? This bottom bar is in, the bottom bar is in compression, right? For a cantilever, whatever bars we provide at the bottom will be in compression. So, if that is the case, you have to increase the bond stress by 25%. So, what we have done over there, you have the value tau BD from the table as 1.2. It is a deformed bar, so we have increased its value by 60%. So that we have multiplied it by 1.6. Then it is in compression. The bar is in compression. So you have to increase its bond stress by 25%. That is what is mentioned in the code. 25% കൂട്ടണമെന്ന് പറയുന്നത് അല്ലേ? So what we have to do?
Sir.
We have to multiply it again by 1.25. So we have tau BD as 2.4. 1.2 into 1.6 into 1.25. So that equals 2.4. But in the previous case, it is a bar in tension. So we had to multiply only with by 1.6. But 1.6 on the mass multiply. Okay. So this is the tau BD for. This is a tau BD for bars in tension. Okay. Okay. Is that fine?
Yes, sir.
Okay. So now I'm going to take you to another portion. That is, if you go back into the code, there is something called a curtailment of tension reinforcement in flexural member. Curtailment of tension reinforcement in flexural member. That's what we are going to discuss next. Okay. Right. So if you take beam, for example, we will take a simply supported beam. Okay. It's being supported over some wall. Imagine that it is being supported on wall. Right. Yeah. It will be having some load acting upon. W per meter. Right. We'll have a look into its bending moment diagram. I'll mark the center of support. Right. This bending moment diagram will be something like this. It will be having a maximum towards the center. Right. Right. So it will be having a maximum at this particular location. We'll take this as its center midpoint. Right. This is its end. So what you can do is you can design for a mu. You can design for a mu, and you can provide the reinforcement like this, right? You can provide the reinforcement throughout. Sorry. So this will be your AST based on the mu that is calculated. But let me ask you something. This is your AST. Is it really required? Is that really required for the entire length of the beam? For example, your AST is 4 number 16 mm hash. Is 4 number 16 mm hash required throughout the beam?
No, sir.
Never. Why? Because your when it goes towards the support, your bending moment is reducing. So you don't require that much of reinforcement. You may have to provide only the minimum AST, right? Maybe you can provide a minimum AST of 2 numbers 16 mm hash throughout. Let this be AST minimum. Definitely, this value, this much reinforcement may be required throughout. But at some location you can avoid at some particular location. That is, we'll take it as a mu2. Let this be that particular location, mu2. That value will be there on either side of your beam. That is mu2, right? mu2. So corresponding to that, I am drawing the section. Okay. Corresponding to these locations, I am drawing the section. you beyond this section, that is, I'm marking it as x, or we'll mark it as y, that will be fine. Y, and y. Beyond this need, as per MU2, you may have to provide only the minimum reinforcement. So beyond this, you can curtail the reinforcement, right? Or this will be 2 numbers 16 hash, right? This could be 2 numbers 16 hash. Here also you need to provide only 2 numbers 60 hash, right? But over here you need a 4 number 60 hash. So how to, or whether you could stop it over here. That means if you are providing the bar, whether you could stop it over here. The 2 numbers of bar could be, that is, you have, for example, you are having all the 4 bars over here. You are having a 4 bars over here. You will lay the 4 bars up to here, right? So you are having the 4 bars over here. The remaining 2 bars will be available over here, right? So what you could do is you can curtail it at this location, okay? But actually we won't be able to curtail it at this location, because this is your critical section up to which you need a 4 number of 16 bars, right? You need 4 number of 16 bars up to this location. So what do you have to do? You can't curtail it over here, but what you have to do is you have to extend this bar to some length, and you have to extend the bar to some length, and then you have to curtail it. Okay, you have to curtail it, right? So what will be this additional length? What will be this additional length? What will be this additional length? Can you tell me? Hello? Hello? Are you there? Hello? Can you give me a reply? Yes, you have to provide LD, right? You have to provide some length addition, and that is what is called your LD, right? Or whatever matters that are related to that is given in this clause, that is clause 26.2.3. So refer clause 26.2.3 for curtailment. Okay, that's for clause 26.2.3 for curtailment. So that is whatever related to that is mentioned over here. That is from clause 26.2.3.1 up to clause 26.2.3.4. Okay. So please go through these clauses. And with respect to positive moment reinforcement, if you are talking about positive moment reinforcement, that is in the case of a simply supported beam, or or if it is a continuous beam, we will be talking about the midspan moment, midspan reinforcement, right? Or to the midspan, you need to provide a positive reinforcement, and towards the support, you need to provide negative reinforcement, right? Positive moment reinforcement will be available at the midspan. Negative moment reinforcement will be available at the support. Positive moment reinforcement has to be provided at the bottom. Negative moment reinforcement has to be provided over the top of the support. Right. I hope you know the concept behind the positive reinforcement as well as negative reinforcement. Ariyathille? Yes, sir. I hope you know. Right. So for that you need to provide LD, right? So at the support you need to provide this at least 1/3 of the positive moment reinforcement in simple numbers and 1/4 of the positive moment reinforcement in the continuous member shall extend along the same phase of the member into the support to a length equal to LD by 3. So that is the concern that talks about the reinforcement at this particular location. That is, at this particular location, you have to take it to a distance of LD by 3. Okay, at this particular location, 1/3 of the reinforcement has to be taken for a distance of LD by 3 beyond the support, beyond the right, shall extend along the same phase of the member into the support to a length equal to LD by 3. Right. When a flexural member is a part of a primary lateral load resisting system, both the reinforcements are required to be extended into the support as described in A shall be anchored to develop its design stress in tension at the face of the support. Okay. Then, at simple support and at point of inflection, positive moment tension reinforcement shall be limited to a diameter such that LD computed for FD by equation 26.2.1 does not exceed a value, right? That is, this value is given over here, M1 by V plus L naught, M1 by V plus L naught, and that is explained over here. What is M1? M1 is the moment of resistance of the section, assuming all reinforcement at the section to be stressed to FD. Right, FD is 0.87 Fy. And V is the shear force at the section due to design load. V is the shear force at the section due to design load. L naught, it is the sum of anchorage beyond the center of support and the equivalent anchorage value of any hook or mechanical anchorage at simple support and at point of inflection. L0 is limited to a effective depth of member or 12 phi, whichever is greater. You have to take either it as effective depth of the member or 12 phi. L0. Your L0 should be D or 12 phi, whichever is greater. That's what it mentions. You have some explanation over here. I'll tell you about this further. Don't worry. To understand this, we will do a problem. Okay. We will do a problem. So please note this question. I have a question over here. I hope your screen is clear. Are you able to see? Can you see this? Can you see this?
Yes, sir.
So please write this question. We'll do it. shall I pass on to the open board? Have you noted the question? Okay. So you are having a continuous beam. I'm drawing the continuous beam over here. Okay. You have the supports like this. How will be your bending moment diagram for this kind of a beam? If you are having UDL over it, these are the support locations. Your bending moment diagram will be something like this. You will be having positive value at the midspan and a negative value towards the support. So you have your diagram like this. Alright. So you have the positive value, you have the negative value, like this, right? This is here BMD, right? So what all are the points of inflection, or what all are the points of inflection? You have the points of inflection over here. So this is a point of inflection, this is a point of inflection, this is another point of inflection, and this is another point of inflection. So you can provide the reinforcement like this throughout. Right. But at these particular locations, you may have to, or you can restrict it, right? This is one location. This is another location. Right. So these are the midspan, right? These are the, you can say these are midspan. Over here you need to provide your total reinforcement, right? That is for number of 16 mm hash will be provided to this region. For number of 16 mm hash will be provided to this region. So beyond this line, you need to curtail your reinforcement. So what is the length that is to be provided? That is what you need to compute. So what will be the LD that you need to, what will be the LD over here? You need to find out. Can you please compute the LD? We need to find LD. Please find out the LD for this. You are using M20 concrete and Fe415 steel, right? M20 concrete and Fe415 steel. So compute LD for the same. Please find it out. What will be your top ED? What will be your top ED? Can you tell me what your top ED is? It is M20 and it is provided for, and you are using HYSC bars. It will be 1.2 into 1.6, so that will be equal to 1.92, right? So 1.1.2 into 1.6. So that equals is it coming as 752? Yes. So that will be 752 mm. Right, that is your LD. Now you have to check. You have to check for this. That is, you have seen expression in your curtailment, right? So for positive moment reinforcement, as per the point 3, your LD computed for FD should not exceed something. That's what you have to find M1 by V plus L naught. So LD should not be greater than your LD should not be greater than M1 by V plus L naught. Okay. So what does M1? Can what is your M1? You need to find M1. We shall see the computation for M1 as well as V. Is the V given to you? Yes, your V is already given. You have, it is subjected to a factored shear force of 300 kilonewton. Right. It is subjected to a factored shear force of 300 kilonewton. So V is known to you. We have to find V is 300 kilonewton. Now what is M1? What is M1? Your AST is 4 number 16 mm hash, right? So what is that equal to? Can anyone let me know? 4 into 5 by 4 into 16 square. Can anyone give me the value for that? $804, right? So that is 804 mm square. Agreed. So what is mu for? What is mu corresponding to this AST equal to 804 mm square? Can you find it out? Your B is given to you as your B is given to you 300 and D is 500. Okay, your B is 300, D is 500. So what is your mu? Please find mu. Mu equals, you can use the formula given in your code. That is in Annex G. You'll be having some formula over there. You can use this formula. Mu equals 0.81 Fi AST into D into 1 minus AST Fi by BD. Please find out and get me the value for mu. Please get me the value for mu. That is Annex G. From Annex B. Please let me know the value. And that will be equal to M1. Your M1 equals 128.99. So you can take it as 129 kilonewton meter. So your, and what is L naught? L naught is D or 12 phi, whichever is greater. Which is greater? Is it D? D is 500. Your 12 phi. What is 12 phi? 12 into 16 is just 192. So your D is greater. So your L naught will be equal to 500 mm. So your LD so 129 by 300 M1 by V plus L naught is 500. So that equals 129 by 300 plus 500. See, you have to take care of your units. This is in kilonewton meter. This is in kilonewtons. So whatever you get, it will be in meter, and this is in millimeter. Okay, so please take a note. So that equals 430 plus 500 equals 930 mm. If the condition satisfied, your LD is not greater than M1 by V plus L naught. Am I right? So condition satisfied. Right. So this is a check that you have to do. Right. See, so that is a problem. I hope it is clear to you. If you have any queries, please ask. Okay. I need to clarify one thing, that as per your see, over here I was explaining, I was telling that you have to take care of this one. The value of M1 by V in the above expression may be increased by 30% when the ends of reinforcement are confined by compressive reaction. So that's what I was explaining. If supports are having compressive reaction, this expression will become like this: LD should not be greater than 1.3 M1 by V plus L naught. So you have to include a factor of 1.3. That's what it means. Okay. So please take a note of this. This one. Value of M1 by V in the above expression may be increased by 30% when ends of the reinforcement are confined by compressive reaction. I'll show you a figure. See. This is what I was trying to explain. See. Please see this. See, if it is confined by a compressive reaction, if the support is something like this, your LD should not be greater than 1.3 M1 by V plus L naught. If it is not confined by a compressive reaction, that is, if the reinforcement is at a higher level from the support, then your LD should not be greater than M1 by V plus L naught. Is that fine? Am I clear to you? I hope it's time for us to stop because it exceeded to a time of 10 minutes extra. Right? Shall we stop? Srilakshmi? Hello, Srilakshmi? Hello?
Yes, sir. Keka.
Are you able to hear me?
Yes, sir.
Is that fine? Shall we conclude for now?
Yes, sir.
So if you have any doubts, please communicate to me.
Sure, sir.
I'll share the video. I'll share the meet recording. Okay.
Okay,
I
sir.
hope some of you may not be able to join the session. So for that, I will share it. And once you go through it, I'll be giving you a problem based on which you have to reply me. Okay.
Okay, sir.
Is that fine? Sure. Okay, fine. Bye. Thank you for the day and have a nice day.